Well, hello again. I'm going to say you're an expert at Lewis structures. Last couple of presentations have been all Lewis structure all the time, and now you're an expert, right? Right? Answer affirmatively. Yes, with confidence. Yes, I'm an expert. Okay, good. Now that you're an expert, and we agree on that, it's time to use our Lewis structures for good and not evil. And the good is VSEPR, as it is pronounced. VSEPR will allow us to predict the shape. I don't know why I have a question mark at the end of that. Predicting what shape will a molecule take? Anyway, all right, moving on. So it's going to be predicting the shape that a molecule will take, period. End of story. So the VSEPR model, what the heck does VSEPR stand for anyway? Anybody want to take a guess? Take a guess? I'll stop talking for a second. You take a guess. Pause the video if you need. Did you guess? Okay, good. Here's what it stands for. Valence, shell, electron, pair, repulsion. Ooh, that's a good word. One of my favorites. So valence, shell, electron. So we're talking about valence electrons, electrons in the outermost energy level. We're talking about how electron pairs repel. Repulsion means repel. So it makes sense, right? Two negative things will repel each other. So what VSEPR is all about is predicting the shape that a molecule will take, assuming that electrons really don't want to be close to each other. Like, hello, they're all negative. So why would a bunch of negative things want to hang out next to each other when magnetically that doesn't make sense? So as it says in yellow, these electron pairs will go as far away from each other as possible. So this is going to be where all these angles come in, and you're talking about three-dimensional space. Basically, what is going to happen is that the atoms, as well as the electron pairs, will arrange themselves to create stability. Man, that's about the 1,000th time we've talked about how chemistry favors stability, right? So you just want to think about, if you're going to attach a bunch of things to a central location, they're going to try to spread out as much as possible, and that's in three-dimensional space going to create angles and all this other fancy stuff. So that's the basics of what VSEPR actually is. So steps for predicting what the shape of your molecule will actually be will require you first and foremost to do what you said you were an expert on, draw a Lewis structure. Once you draw a Lewis structure, you need to do some counting. So you will count the number of bonded electrons, which basically that's just attached atoms. How many attached atoms do you have? And then also count the number of lone pairs, and this is all about the central atom. So I don't care how many electron pairs might be around a chlorine attached to a carbon. It's all about the central atom. When you get started doing this, one of the questions that always comes up is, well, is a single bond and a double bond and a triple bond, will they be treated differently? No. Count multiple bonds as one bonded electron pair. So if you have a single bond, it counts as one attached atom. If you have a double bond, it's counted as one attached atom. If you have a triple bond, one attached atom. Step 3, think. What arrangement of atoms and lone pairs will allow for the least electron repulsion? And my simple way of saying it is you want to give each thing, whether it's an electron pair or an atom, the most space possible. This is all about, this is all about understanding that you've got to give things space, and atoms, that is, they don't want to be crowded next to each other, and this again because of electrons that are in valence. So one really special note that I have to make with you is about lone pairs. So bond angles and the effect of lone pairs. To say that what's on this slide is important is a very big understatement. It's important. You need to know what's on this slide. A lone pair needs more space than a bonded pair. So that means that if you have those two little dots around a central atom, that's actually going to take up way more space than having a hydrogen or a chlorine atom attached to the central atom. Why? Why? I want you to ponder this for a second. Two stupid little lone electrons take up more space than a whole atom? I mean, let's be real. This does not make sense. This does not make sense at all. An atom is way bigger than two baby stupid little electrons. Why? Any thoughts? Any ideas? I'll tell you the answer. Obviously, you can't respond to me. A lone pair of electrons is attracted to only one atomic core. That would be the central atom. Whereas a bonded pair is attracted to two. Okay? Two atoms hold an electron pair in tighter. Okay. A lone pair, and this is the one I really like, a lone pair is reaching out, searching, my phrasing, for another atom to bond with. I kind of think of a lone pair as just this thing, and it's just like, all I want to do is have an atom to call my own. And then all it does is it's literally reaching out, trying to grab a hold of any passing atom it possibly can. And so by reaching out, I mean, if you extend your arms out from your body, yes, I'm doing it right now. When you extend your arms out, you take up more space, don't you? Yeah. So what happens is when this lone pair is throwing out its arms, reaching and grabbing and trying to find something to bond with, this pushes other atoms away. And it actually gives that lone pair way more space than really what it needs. But it's because of this sort of neediness. I mean, you can think of a lone pair as this, poor little kid that just wants to be loved. And he's going to reach out to anyone who will just give him love. Man, chemistry just turned into a soap opera. Okay, so anyway, important. To me, I feel like it's the last two bullet points that really start to give the description of what's going on. So, maybe really focus in on those last two bullet points. So if we have an understanding about how electron pairs take up more space, and all of this VSEPR stuff, all of this molecular geometry is stuff that you should have learned last year, so this really should be a review. But you will definitely need to make sure that you memorize these things very well, because these are going to show up on the AP exam, guaranteed. So, picture time. So we'll start off with the easiest ones. If you have linear geometries, so we basically are saying we've got a 180-degree bond angle. We have a central atom, which is shown in red, and then these appendage atoms sticking off of it that are shown in green. And what they're showing you here is that if you only have two things attached to a central atom, well, they're going to be in a straight line, linear. So I think that one definitely makes way more sense. Don't worry too much about what you see here in this electron pair geometry. That's going to, I think, maybe confuse more than anything, so don't pay too much attention. Next, the three attachments. So you have a central atom with three attachments. So notice here, when you have three bonded attachments, the best way to get these three things as far apart as possible is to put them in a single plane, hence the word planar, and it's a three-pronged kind of an organization. So that's where the word trigonal or tri comes from. So trigonal planar, three things all in one plane, and they have a 120-degree bond angle. And again, that would all be in one plane. You're separating 360 three times, 120, 120, 120, and that's how they stay far enough apart. Now, an option for this is what you see here with the bent configuration. So please note, I still have three things attached, right? I have two bonded atoms, and then I have a lone pair. That's three attachments. So you can see within this bent structure that you kind of have this idea of trigonal planar. However, when it comes down to assigning molecular geometry, it's about the atoms. So what you want to understand is sort of like a comparison. So look back up here at the linear. You've got two attachments, and down here you've got two atomic attachments. But here the difference is the extra electron pair. So in this case, these two atoms are perfectly in line with each other, 180-degree bond angle. But in the bent configuration here, notice that the issue is this lone pair. So what the lone pair right here is going to do is it's actually going to push those other two atoms down and away from it because it wants more space. So it pushes this into a 120-degree bond angle between the atoms instead of what you may assume as 180 because there's only two atomic attachments. So hopefully that starts to really make some sense with what we talked about on the last two slides about they need the most space possible, but they also have to take into account the electron pair and the impact of the electron pair. So again, we push away those two atoms out of the 180-degree bond angle and down into the 120. So I want to make sure that you understand here, there are actually going to be two different ones that are going to get the bent designation. There's a bent that has a 120 degree bond angle. That 120 is when there are 3 things attached. So 2 atoms, 1 lone pair. The other bent comes here, which you can actually see down over here. So we'll get to that in just a second. Okay, so moving up to 4 attachments. When you have 4 attachments, you are going to be what's called tetrahedral. In fact, this may not look like they have equal area in between them all, like equal bond angles, that is. It looks sort of like this guy has way more space, but that's not true. In fact, they all have 109.5 bond angles, and that's because it's in 3 dimensions. So it may be important at this point to really start talking about what some of these notations mean. Like, for instance, when you look here, you see a straight line, and you see a straight line, and you see a dotted line, and then you see something that's called a wedge. And what you want to understand, yeah, I'll get to the bent thing in a second. Sorry, the animation, this is what I want. So recall, this is something you should have learned before. A straight line means that you're in the plane of the page. So this one is going straight up, and then this one is coming straight out, like if I was holding a piece of paper. This, the top one here would be on the piece of paper, and this would be on the piece of paper. The dotted line means going back into the page. So this one is going like back into space, and the wedge means it's coming out at you. So this is like popping out, like think 3 dimensions. So lines mean you're in the plane, dotted means going backwards, and wedge means coming out at you. So this is your tetrahedral geometry with 4 attached atoms. Now notice the variations. Here you now have 3 attached atoms and 1 electron pair. And here you have 2 attached atoms and 2 electron pairs. So again, the effect of the electron pair is that it's going to push atoms out of the previous angles that we saw. Because if you go back to the previous page, if you have 3 attachments, you should be trigonal planar. You should have a 120 bond angle. Well, here we have 3 attachments, but 1 lone pair. So we don't have a 120 bond angle. Instead of these guys being trigonal planar, what happens is the lone pair pushes down on those atoms. It causes a trigonal pyramid. So think 3-dimension pyramid, a 3-sided pyramid with a 109.5 bond angle. Okay, the bent is then just a variation of that, but it's a bent at 109.5 because there are 4 total attachments, 2 atoms, 2 electron pairs. Okay, so that's your second bent configuration that you would have to worry about and keep in mind. The key to understanding which bent you're talking about is, are there 3 attachments? It's bent 120. Or are there 4 attachments? And that's bent 109.5. Okay? All right, so moving on to the lower section here. So when you have 5 attached atoms, you have now something called trigonal bipyramid or trigonal bipyramidal. What you can see is around the center, this is basically a trigonal planar geometry. And then going up and down, this is a linear geometry. So it's basically like you're taking that central atom and you're sort of putting a couple things together. So that's why they're offering you 2 angles here. Notice that the 120 is pointed right here, which would be around the center. That would be your trigonal planar geometry. And then the 90 is from the center up or from the center down, from any of these. In 3 dimensions, that would be a 90-degree bond angle. So when you start to mess with this configuration and remove atoms and replace them with lone pairs, you can see now 3 different variations. You can see a sawhorse, also sometimes called seesaw, which is usually what I've ever used to call it. That's how I learned it, was seesaw. And it's a seesaw because if you can imagine, these 2 things are legs, and then this is like the teeter-totter. So you got to look at it sort of sideways. So imagine a butt sitting there and a butt sitting there, and then you can teeter-totter back and forth. Well, teeter-totter is a seesaw. So kind of makes sense. You also see this one, which is called T-shaped. So you can see the up and down linear portion, and this is coming out of the plane at you, or you can have it go side to side. That's fine too, but you have a literal T-shape with 90-degree bond angles between atoms. And then your final option is your linear. In which you create your 3 lone pairs around the middle, and then you have an up and down linear geometry of your atoms. Now, one thing you may have a question about is about the addition of the lone pairs. So did you notice that the lone pairs were always put into what's called the equatorial positions as opposed to the axial positions. Okay, so think about this. If I go back over to this, around the middle, think equator, like make a circle with this whole thing, make an earth. So around the middle, that's the equator, and then up and down, that's the axis. So when they add these lone pairs in this trigonal pyramidal overall geometry, they're adding them to the equatorial positions instead of the axial, and that is because there is more room. Okay, remember, around the middle, that's 120 bond angle. Up and down, you've got 90. So at least in the middle, you get 120 degree separation between the middle ones, and that's a little bit of a better situation. So that's your 4 attachments. Okay, finally, we move on to 6 attachments, and this overall, when you have 6 attached things that are all atoms, it's called octahedral. The octahedral idea, basically think it's like it's 2 pyramids, 2 4-sided pyramids, one on top of each other. In the case of here, like imagine this is your upper point of your pyramid, and connect a line down to each one of these, and that gives you your upper pyramid, and then do the same thing on the lower, and you've got a lower pyramid. Octa, the 8, comes because there are 8 sides in total on this structure. So octahedral, everybody's got a 90-degree bond angle. Okay, that's left to right, that's front to back, and that's top to bottom, so everybody's 90 degrees. And then you can see the 4 variations as you begin to change by removing an atom and adding an electron pair. In each case, we're still putting them on the equatorial positions, but we don't have to. In fact, we don't have to because everybody's got 90 degrees, so it really doesn't matter at this point. But it does bear sort of re-mentioning that in the previous geometry with the trigonal bipyramid, there was more space by putting the lone pairs in the equatorial position. So it makes more sense to do it now also. So just kind of keep it standard, okay? So you have square pyramid, because in this case, it's a pyramid on its side on the way that the picture is shown, but take this and connect my lines out to my other atoms. Give me my cursor. There we go. So this is a square pyramid. Okay, this is square planar, meaning a square, 4 things, and they're all in the same plane. And then this is T-shaped, another T-shaped, and still 90-degree bond angles, and then we also have another linear. Okay, so with these, if you have questions, definitely bring these back to class tomorrow, because with a lot of this, it really does come down to being able to visualize it. And so I have some things that we can work with to visualize. We can also look at other pictures on the internet to try to help us out too. So if you have some questions about this, just let me know. And as a final thought here, VSEPR's great. You know, VSEPR allows us to predict molecular geometry, but please note, only allows us to predict molecular geometry. So we can come up with a pretty good idea of what we think is going to happen, but in reality, what's really going to happen, if we want to know the real molecular geometry of something, you're going to have to do it through experimentation. You're going to have to take the actual molecule, do some stuff with it in the lab to determine the geometry. And the reason why this might work is because of charges. It's because of polarity. When you go and you look at these molecular geometries, what they end up doing is creating polar molecules. And so if I have a polar molecule and I put it within an electrical field, that electrical field will impact the molecule. For those of you that had me last year, I proved to you that water is indeed polar because I put some static, well, somebody in your class. Actually, I'm sorry, this is from biology. So if you want me to do this demo tomorrow, let me know. But somebody in biology, if you had me in biology, I had somebody put static electricity on a balloon, and I was able to bend water with it. And that's because water's polar, and I created an electrical field, and it bends. It impacts the water. So that's proof that water is, in fact, a bent configuration, because that leads to polarity. So I do say here, we'll talk about this next in depth a little bit more. There is actually, as part of your homework with this section, an online simulation of VSEPR, so I think that will help a little bit also. But as far as the electrical fields and as far as the polarity of molecules, that is for the next presentation. So that's it for today. Again, tomorrow I'll show you a fancy demo, and we'll take a look at some online simulations, and hopefully that will help you out even more. Ta-ta!